Hello everyone, today I would like to continue with the lecture 7, Property and Application of Fourier Series. And this is the outline for today. Gibbs phenomena, symmetry, response of the LTI system to periodic signal, power and Parseval theorem, circuit application. Okay, what is Gibbs phenomena? Okay, Gibbs phenomena is as more and more Fourier components are added, the sum get closer and closer to the original waveform. Okay, if you look at the first man, this is the fundamental sine wave, and then plus with the second person, okay, is another sine wave. The third person also have another sine wave. When you add these three sine waves together, okay, it will come to the third person. Okay, so this is we consider as a Gibbs phenomena. Okay, let's look at this one. This is the DC component. Okay, do you still remember what is DC component? As I mentioned to you in the, you still remember that find the anode, AN and BN? Okay, this DC component is referred to the anode. Okay, and the AC is the AN and BN. Okay, so anode refer to the DC. Okay, AN and BN refer to the AC component. So this is the fundamental AC. If you look at this one, it's a fundamental AC, just like the first person. Okay, AC. And then you have the two AC component. Two AC component is a combination of two fundamental signals. Then you will get a two AC component. And what about three AC component? Means that you have a combination of three AC component. So this is only one. You combine two, you get this one. You combine three, you get this one. What if you have more? Okay, this one if you have a 4 AC component. Okay, this one is 5. When you get more AC components, okay, it's nearly goes to the original signals. Means that it's a square wave. Okay, it's a square wave. Okay, similarly, if you look at here, this is a combination of let's say original is a sine wave, a square wave. Original is a square wave, and is only one fundamental frequency. You have the sine. Let's say if you have 3, this one is a 3 AC component, so you have the square wave, and then you have the sine wave. So it's a combination of 2, and this one is a combination of 3, and this one is a combination of a lot. So this combination of a lot, it will lead to original signals. Okay, will lead to original signal. Next one is a symmetry. Okay, symmetry, you have 3 types. That is the even symmetry, odd symmetry, and the half wave symmetry. Then what is the importance of this property of symmetry? Now, let's look at the even symmetric. Okay, even symmetric said that the xt equal to x minus t is the mirror image at the y-axis. Yes, correct. It's a mirror image at the y-axis. Okay, if you look at this here, the signal xt is at the right side. Okay, and when say that even symmetry is xt equal to x minus t, this means that this part is the refer to the x minus t. So even symmetric is the mirror image at the y-axis. Okay, so you have the signal here, and also you have the signal here if the signal is the even symmetric. Okay, similarly, if you look at this signal xt, okay, so even symmetric, you have the another signal at the left hand side. Alright. Okay. If you look at the Fourier coefficient, okay, usually for the Fourier series, you need to find the anode and Bn. Okay, if you know the property of the even and odd symmetry, you can actually skip some works. Okay, what's mean here? Okay, for even symmetry, you still need to find the anode. Okay, you still need to find the An. But Bn we don't need to find because Bn is equal to 0. But why Bn equal to 0? Okay, why Bn equal to 0? Now, okay, if you look at here, the function of xt is the cos x is an even function. So this is symmetric, right? At the y-axis. Okay, so Bn is referred to the cos, cos theta theta. So if you sum up these cos signals, what is happening? Okay, if you look at here, cos is from here to here, right? If you sum up this one, this part, the green part and the yellow part, actually is cancel out. So when you cancel out, means that it's nothing, it's 0. Therefore, is a Bn is 0. Now look at the odd symmetric. Okay, odd symmetric is x negative t equal to minus xt. So this one is a mirror image at the y-axis and then mirror image at the x-axis again. So let's say this is the signal xt, okay, at the right hand side. Okay, mirror image at the y-axis, so it will goes to here. Okay, this signal will goes to here. And then mirror an image again at the x-axis. So mirror again, so here. So this one actually is a odd symmetric. Okay, odd symmetric. Okay, so if you look at this signal, also the same. Okay, first of all, the mirror image at the y-axis is here, and then mirror image at the x-axis it will turn to here. Therefore, the signal is like this. Okay, so in order to find the Fourier coefficient, for the odd symmetry, a naught is 0 because there's nothing. Even you find anything is 0, you won't have any value because it's always close as 0. So n is 0, and n is also 0, or you only need to find Bn. So if a question given is either even or odd, and you know the property of the even and odd signal, actually you can save some time to calculate the n of an and bn. You straight away you said the properties of the odd symmetric or property of the even symmetric. Okay, let's say property of the odd symmetric, n naught is 0, and n is 0, and you just need to find the bn, which is simple to you. Okay, for a sign, for odd symmetric, y is 0. Okay, you see that this one is a odd function. Okay, it's an odd function. So when you cancel out, okay, this is the sine function. So when you sum up, this green part will cancel out with the yellow part. So when you sum up, it's a 0. That's why you get 0 there. Next is the half-wave symmetric. So half-wave symmetric is like this, only half. Okay, xt is equal to negative xt plus t over 2. For half-wave symmetric, you only need to, for the coefficient part, you only need to find the an and bn. Okay, for a naught is 0, an even also 0, and bn even also 0. So you need to find the an and bn odd part. Okay, where n equal to odd. So next is the summary for the even and odd and half wave, in which value you need to find. Okay, so even you only need to find the a and bn because it's not equal to 0. For odd, you only need to find the bn. For half wave, you only need to find the an and bn for the odd value. The next one under this topic is the response of LTI system to periodic signal. Okay, if ht is the impulse response of a LTI system, then the system response to a complex exponential is a complex and exponential with the same frequency and the change in time. Okay, now look at this one. So the response of the exponential is what? The response to the exponential this is hash f naught, okay, and the exponent j 2 pi f naught t. So hash f is refer to the integration of hash t exponent minus j 2 pi f t dt. And the xt has the Fourier series like this. Okay, xt equal to summation of the xn. This one is looks like a exponential. Okay, expression is exponential. Okay, so hash f is the integration of hash t. So this one you need to remember this. Okay. So as a conclusion for this, so the output, okay, the output of the system is the yt. So yt is the summation of the yn exponent j 2 pi nt over t naught, in which the yn is referred to this one, and the amplitude is this one, and this is the phase. Alright. Okay, this sounds complicated. Okay, never mind. So I will next one I will teach you on the example. Okay, give you an example how the LTL system response looks like and how to deal with that with the amplitude and the phase given. All right, see you. Thanks. Bye.